has begun his career at the UK's Harvard Laboratory, managing research into fast reactors and nuclear safety. His research was mainly on computer modeling on nuclear fuel and radiation damage. In the 1990s, he was involved in the shift of AEA technology to the private sector and then managed their materials and chemistry research. He later spent 5 years in Japan as regional director of Asia Pacific. From 2001, he worked on DTI and UK trade and investment activities as an energy technology specialist. The latter part of this role advised on the investment and supply chain for nuclear new builds. He is now visiting professor at the Dalton Nuclear Institute here at Manchester, where he is involved in nuclear policy development and research on advanced fission and fusion systems. I have joined many of Juan talks. I always learn a lot from him and really enjoy his talks. I'm sure we will hear a great talk from him today. Let's welcome Juan, and we are looking forward to his talk.
Right. Well, I hope you can hear me. This is a very personal subject for me. Not the least is it's not my impact on the history of nuclear science. It's the nuclear reactors and nuclear energy. It's the effect of nuclear energy on me. My parents confided in me that I was conceived on VJ night. And at that time, my father was training for the invasion of Japan in the infantry there at Royal Gloucesters. And my parents were extremely relieved that he wasn't going to have to go and fight in Japan. And the reason, of course, was because of the atomic bombs, which unfortunately fell in Hiroshima and Nagasaki. So let's start with the prehistory. I'm talking mainly about the civil side of nuclear power. But to understand the civil side, unfortunately, we've got to go and learn a little bit about the prehistory, which involves the development of nuclear weapons. You'll see on these slides that some of the names have purple on them. Though all of those people have an association with Manchester University. Usually with one of the predecessors of the University of Manchester and the Victoria University and the University of Manchester Institute of Science and Technology. The first of these, of course, was John Dalton, who we named the institute after. And he was involved with one of the predecessors of the university. And of course, he was the first person to really take the classical, the Greek and Roman idea of an atom and then show that it was a reality and it could be related to the what would become later the periodic table of the elements. That was, of course, solidified by the work of Avogadro and Loschmidt on appointing actual atomic weights and atomic sizes to the elements. And then, of course, Joseph Thomson, who was a student at the Victoria University of Manchester in Cambridge, discovered the electron in 1897. And that was the first step in converting to the atom as a sort of vague thing to it having some sort of structure. Then, of course, Einstein, with his theory of relativity, was able to show a relationship between energy and mass. And as we'll see, that became very important in the discovery of nuclear energy. And Ernest Rutherford was originally in McGill University in Montreal, where he discovered that radioactive decay was split into three main parts, alpha, beta, and gamma. And he came to Manchester in 1907 and stayed for 12 years. And that was an extremely productive time. Now, I've added Niels Bohr's name here with the purple because during that time, Niels Bohr actually came to the university, and because Rutherford had actually, with his team, discovered that the nucleus was had a tiny positively charged ion at the center, and that with a cloud of electrons about it, that Niels Bohr was able to create his first proper theory, a quantum theory of the atom. Joseph Thomson again in Cambridge, together with Francis Ashton, introduced and perfected the mass spectrometry. Now, this is very important because what that meant was we could actually identify the various elements that make up, the various nuclides or isotopes that make up each of the elements and measure their mass. And what they found, of course, was that the mass was not a simple progression of a particular factor, but it varied between different nuclei. And we could then use EmC squared to calculate the binding energy of the nucleus. And that, of course, was an important step because it opened the prospect of perhaps using the energy differences per nucleon in each nucleus and to use that as useful energy. Then, of course, Ernest Rutherford had moved to the Cavendish Laboratory at Cambridge, and they discovered the proton at that time and identified it as the hydrogen nucleus. And this, together with the James Chadwick, another student of Victoria University in Manchester, in Cambridge, discovered the neutron using a reaction. I started life as a physicist as a laboratory assistant, and I went to the scientific assistants training school at Harwell in 1962. Oh, that's a long time ago. And right next to the GLEEP reactor, which was the first reactor built in Britain. And one of the first experiments I had to do as a trainee was to make a neutron source with using alpha particles which come from a polonium decay, using the alpha N reaction on beryllium to generate neutrons. Now, this became an important experimental tool which allowed people to start exploring the influence of neutrons on the nuclei of various elements. So, John Cockcroft, a student at both the Victoria University and the forerunner of the University of Manchester Institute of Science and Technology, went to Cambridge and with Ernest Walton was the first person to split an atom. And this was using a proton irradiation on lithium-7. And lo and behold, what did you get? A bunch of energy. That's a lot of energy that came out of that reaction. And of course, people said, well, why don't we use it? And Rutherford wisely said, moonshine. It's moonshine because to extract that energy, you've got to build an accelerator and you've got to accelerate the protons, which is a really inefficient process, and then extract the energy. So we'll never have nuclear energy. However, Leo Szilard was very much ahead of his time. And he took Chadwick's discovery of the neutron and said, what if there was a neutron reaction? You don't have to accelerate the neutrons, and the neutrons are neutral, so they don't have to overcome the repulsive energy that a hydrogen ion has to overcome in order to interact with the nucleus. So it can be done at very low energies. In fact, as we know now, the slower the energy, the bigger the cross-section is for an interaction. And he thought, let's look at lighter interactions and see if we can have some N2 reactions where a neutron comes in, it breaks up the nucleus and more neutrons come out, and then we could get a chain reaction. And he patented the idea and started looking for these reactions. Well, sadly for poor old Leo Szilard, there aren't any. There are loads of reactions. They all have huge thresholds and they absorb energy. They don't extract it. They don't release it. So he had a useless patent. So he had to sit on his heels for the best part of 10 years before he could actually use it. During that time, Mark Oliphant, an Australian physicist working at Cambridge, actually discovered the fusion and the possibility of extracting energy from fusion. But again, because of the repulsive interaction between the nuclei, you need huge amounts of energy. And as we know, reaching conditions in stars is rather difficult. So sadly, again, no chance of getting nuclear energy. So what happened? The first three teams here in Rome, Paris, and Berlin started using this neutron sources that had been discovered by Chadwick to explore what happened when neutrons went into various elements. All three of them got anomalous readings. When they used mass spectrometers afterwards, after their interactions, they discovered that things like lanthanum and barium were appearing. What was going on? They couldn't understand what was happening. So it was only the shrewdness of Otto Hahn and Strassmann and a lady called Lise Meitner that they actually discovered fission. And what we were seeing were fission products. Now, poor old Lise Meitner, she was Jewish and she had to flee Germany, and she went to Sweden. Unfortunately for her, her environment in Sweden was very prejudiced against women in science and also a little bit of anti-Semitism. She never got a Nobel Prize. Really sad. So she really was the person with her nephew, Otto Frisch. Otto Frisch had gone to England and then he went to Denmark and worked with Niels Bohr. He came and he worked on fission with Lise Meitner in Stockholm, and they got the first real understanding using a thing called the liquid drop model to be able to understand the process of fission and how it might change with different nuclear structures. And that was really the birth of the confirmation that nuclear fission could be a source of energy, because they calculated the energy releases on fission were enormous. As we know now, a couple of hundred MeV to each interaction. Later on, both Leo Szilard in America, he'd moved from Britain to America by this time, and Frederick Joliot-Curie in Paris confirmed that more than one neutron was produced on fission. So Leo Szilard was back in the game, because his patent now had meaning, because there was a reaction that could form a chain reaction. And he leaped in there and he confirmed that chain reactions could occur, and this was important. Now back to London. Again, Rudolf Piles, he was of Jewish extract. He was brought up a Christian, but he had a Jewish background. He had to flee Germany back in 1933. And where did he come? Manchester. And he actually went and spent most of his career in Birmingham University and later at Oxford. And I knew him quite well because working at Harwell, he used to come down and have tea with us in our tea room regularly. So when the first reactor had its 50th anniversary, I took him to Chicago and looked after him. So if we look on in Cambridge, it was discovered that plutonium-239 would be actually better than uranium-235 for making a weapon. And then later, Glenn Seaberg in Berkeley in California just isolated plutonium and started to work on the chemical properties. And then by this time, Enrico Fermi and Szilard were in Chicago, and they made the first nuclear reactor in December 1942. So this is what was going on. The discovery was in Germany. The German project started almost immediately to look at, once they'd got information from what was going on in Sweden and in the UK, and they made a mistake. They realized that they could use either graphite or they could use heavy water as a moderator, because as you reduce the energy of the neutrons, the cross-section goes up and it's easier to build a reactor. However, in Germany, all the graphite sources were contaminated with boron. And as we know, that one of the isotopes in boron is a heavy neutron absorber. So they gave up on graphite. So they invaded Norway, of course, and they took over the production of heavy water and were looking to use heavy water as a moderator. However, the work of the Norwegian opposition to the German invasion captured and sank a ferry with the whole supply of heavy water. So they didn't have any more heavy water either. So what happened was the Germans had to realize that their project was not going to work. However, Rudolf Peierls and Otto Frisch wrote a letter to the UK government indicating that they should start developing a bomb because they were pretty sure that the Germans would make a bomb. So the work started in the United Kingdom before the United States. However, the intervention of Einstein and the Fermi and people like that put pressure on the American government, and by 1942, the Manhattan Project was started, and the British moved all of their effort to the United States. And as we just said, the first reactor was initiated in 1942, which was a graphite-moderated reactor cooled by water. And the result was that in early 1945, the first atomic bomb exploded, and then unfortunately 2 were exploded in Japan. In 1945, the Americans passed a law which prohibited the transfer of information to any other country, including their partners in Britain. Before that, the situation in the United States was getting dodgy. As they saw that it was possible to make a bomb, with a huge contribution from British people. For instance, the explosive lenses to compress the plutonium were invented by British people. So the British put a lot of effort into it, but they were suddenly cut off from the information and had to move to Canada. And then later they moved to Harwell, where they set up the program in the UK in 1946. And by that time, the British had their first bomb in 1952. However, we gave the Russians a gift, which was Klaus Fuchs. Klaus Fuchs was on the British program. He was an associate of Rudolf Peierls. He didn't ever work at Harwell, at Manchester, but he, when he came back and started working at Harwell, he was transmitting all the information that he'd got from his work while he was in the United States to the Russians. And the Russians were, the Soviets actually made their bomb in 1949. So that's the prehistory. So let's concentrate now on the civil aspects of it. Next one. Right. The reactors that would be eventually developed for production of nuclear energy were based on the reactors that were used to generate the plutonium for making nuclear weapons. And they were called piles because the first reactor was literally a pile. It was lumps of graphite with lumps of uranium spaced between it and built up into a big mass. Later, the plutonium generating reactors were again huge masses of graphite with long tubes where uranium was pushed in, irradiated for a short period so you didn't get too many higher isotopes of plutonium, and were then pushed out the other side and then processed to extract the plutonium for the weapons. The UK, the ones at Hanford, which made the American bomb material, were cooled by water. In Britain, we also had similar piles to these, but they were cooled with air. Because of this, the UK became interested in gas-cooled reactors with moderated by graphite. So next slide, please. So what were the first power generating reactors? In fact, the first significant one was actually a fast reactor. It wasn't a graphite or water moderated reactor. It was EBR-1 fast reactor in Idaho, and it generated small amounts of electricity to demonstrate nuclear power as early as 1951. But it was not until 1954, which at Obninsk in Russia, that a significantly large reactor. This one was based on plutonium production reactors. It was cooled by water, and steam was generated in the reactor to generate power, and that was put on the grid for the first time in 1954. So that's really the start of nuclear power. The first proper power stations were at Calder Hall, and these were Magnox reactors, and these were graphite piles, uranium metal fuel in magnesium oxide alloy cladding. And each one produced 60 megawatts electrical, and there were 4. They were dual purpose. Their real purpose was to make plutonium. And also the ones at Chapel Cross in Scotland were also dual purpose reactors. In fact, Britain made so much plutonium, we provided most of the plutonium for the American weapons system as well. And not many people know that. So these graphite piles were cooled with pressurized carbon dioxide, as I said. At the same time, there was an interest in marine propulsion, and it was realized you're not going to put a graphite pile in a ship. They're huge, and they're very heavy. They have very low power density. It's fine for making plutonium for weapons, absolutely no good for driving a submarine. However, providing you had access to enriched uranium, you could use water, ordinary light water, to cool the reactors. So next slide. So I put the 4 main countries that initiated nuclear power programs. Of course, France also played a major part in this, but they tagged on a little bit after the British and actually had a very similar start to the British on this. In Britain, we made the Magnox reactors, which were graphite piles cooled with CO2. The French then also produced similar reactors, and they built some of them in Spain, and we built Magnox reactors in Italy and in Japan as well. And this was really the birth of the growth of nuclear power as a common thing. Americans very quickly after that started to use the submarine programs to look at ways of making reactors which were much smaller and more compact, but they needed enriched uranium, and the PWRs and BWRs were born. The first BWR was the Dresden reactor in about 1960, and the shipping port PWR in around the same period in a few years after the first submarine reactors were launched, which was in the late 1950s. And there's a sort of dividing line here, and this was marked by a conference in Geneva, where the swords into Ploughshares comes from. The idea was that they would have a conference and agree that the military programs would be separated from the civil programs so that there could be exchange of information. And that was initiated by Russia, actually. And because of that, all through my career in the 1960s and 70s, I had contact with Russians, and I had to learn Russian because that was a common language that to communicate in the nuclear communities, and particularly on fusion. We created the Culham laboratory next to Harwell, so it could be separate from Harwell, where maybe there was a little bit more secret work going on. But it could be an open laboratory where scientists could come from Russia and work, as well as scientists from Britain and America and other places. The Soviet Union started with graphite-moderated boiling water reactors, which are BMK reactors. And of course, the most notorious ones of those, the four at Chernobyl, where I'll introduce what those reactors are in a moment. But they had a different sort of a program until they started what they call the WWII program, which is basically PWRs, copies of the American submarine reactors, and then copies of the American commercial reactors. Around that time as well, because of the availability of heavy water in Canada, and the Anglo-Canadian and French work in Canada started with experimental reactors using heavy water coolants. And from that came the CANDU reactors. Now, I don't know whether I'm insulting your intelligence by putting this up. I don't know how many people actually know what a reactor looks like. This is just to show you the PWR. You have a separate steam generator. So you're heating up the water here. It's pressurized to prevent it boiling. And that goes into a steam generator. You have something which controls the pressure here, called the pressurizer, and then you generate the steam that then is used to drive the turbines and generate your electricity. The fuel is in long rods of uranium dioxide clad in zirconium alloy, very long, 4 meters long. Next one. Now, this is a BWR. How much simpler? However, we've lost 1 degree of containment, because what's happening here is we're boiling the reactor, boiling the water inside the reactor, and this is driving the steam up into the turbines. This should have been yellow as well. I don't know why it's blue. So basically, it starts blue and changes into red. Pretend that it's the other way around, and so you're putting the steam through the turbine, and that's a BWR. Next slide. This is the CANDU reactor. Now, this is quite different, and it hankers back a little bit to the plutonium production. We've got a separate tank with the water in, the heavy water in it for doing the moderating. That's called the calandria, and we have pressure tubes. And the fuel is in bundles, short bundles, just like when you're making plutonium for weapons. They're shoved into the pressure tubes, and gradually, as they're burnt up, they move through, and then they're taken out the other side. And you have a separate coolant, again heavy water, which flows through the pressure tubes. So the calandria is kept at quite low temperatures, but all the heat is in the pressure tubes, and that is then used to heat ordinary water in steam generators, which then generates electricity. And then advanced gas-cooled reactor. This is most of the power which is produced in Britain at the moment. And they were advanced. They just had an unfortunate history. Graphite moderator. The fuel is in bundles of stainless steel UO2 fueled rods. We have the carbon dioxide goes, there's a concrete pressure vessel. It goes through a steam generator, generates the steam. Next one. And then finally, the RBMK reactor. Again, we have the graphite. We have pressure tubes. The fuel is in bundles, this time with zirconium niobium alloy channels and rods, and then the water is pumped into the pressure tubes, and it then generates the steam in the channel. Steam comes out, is separated, and sent off to the turbines. So it's a sort of boiling water reactor with a graphite moderator. Right, these are the 8 or 10 designs. 1, 2, 3. Anyway, we see that pressurized water reactors and boiling water reactors are the dominant ways in which electricity is produced. And most of the reactors and power reactors in the world are of those designs. Quite a few CANDU sorts of reactors. The main advantage of the CANDU reactor, as in the case of the Magnox reactors, you can use natural uranium in them because the heavy water moderator doesn't absorb many neutrons. And so these have been quite successful as well. Next one. Right, so what about the size of the reactors? So in the beginning, they were all little. These are called the Hall reactors here. So these are only reactors that go onto the grid. So it's doesn't include reactors for submarines and things like this. So it's all civil reactors. And you can see that the British ones were the first ones that really were not experimental reactors, but actual power stations. But then very quickly, as we come into the 1970s, the power of those reactors is starting to approach 1 gigawatt. This is 60 gigawatts of electricity to 60 megawatts of electricity compared to 1,000 megawatts of electricity per reactor. And in the 1970s, huge numbers of these reactors were built. And as we move into the 1980s, most of those reactors are above a gigawatt. So we call them gigawatt reactors. And as we move out, I think if we press again, we might get, oh, could you put back this? No. I thought there would be an indication of what happens. That'll come later. So we reclassify reactors now as large reactors if they're above, I don't know, 400 or 500 megawatts electrical, or in the IAEA scheme, 300. Small reactors that are below 400 or down to 300, to levels of about maybe 50 megawatts electrical. Below that, we call them microreactors. You can see the different countries here. These ones here are Russian reactors in the Soviet Union. They're 440 megawatts electrical. Why? Because they wanted to transport the pressure vessels on trains, and yet they had to go through the railway tunnels. So they were limited in the size that they would have them. However, they also limited the size in the resulting in the neutron load on the reactors was rather high, so the life of the reactors was quite short. So one of the projects I was involved with the Russians was trying to solve the problem by annealing the reactors. And it's really a very force majeure to do this. You take everything out of the reactor, you put in a big induction heater, and you heat the pressure vessel up to about 800 degrees centigrade. And then the radiation damage is annealed out, and then you can put the reactor back together and use it for another 20 or 30 years. Next slide, please. These show you what countries. There are now about 40 countries that have power reactors, either constructed or about to be constructed. If we look at the United States, we see that maybe about a third of the reactors that are built are now under decommissioning. So they've lived their lives, and they haven't built any very recently. Just one, which is under construction at the time that this was done, and that's the Vogtle reactor, Vogtle 3 reactor in the United States. We see in China lots of reactors under construction, no reactors under decommissioning. So the ones that first went into power were the Daya Bay reactors, which I think were in the early 1990s. And the UK actually provided the steam generating systems for those reactors. But now China is self-sufficient. French, of course, had a huge program of PWR construction in the 1970s. Russia, also quite a few. UK, most of our reactors, all of our Magnox reactors are now closed, and quite a few of the AGRs are closed. And the only active construction project is Hinkley Point C. Right, so we see these are the dates at which the reactor comes on power. And you can see that in the 1970s, there were a lot, and also in the 1980s. However, there's a story behind this. Just press again. Right, we had accident in 3 Mile Island. At that time, these reactors were under construction. Because of the accident at 3 Mile Island, the construction was stopped by the US NRC, and the safety cases for all of those reactors were revised, and then their construction was restarted, and they came on power late as a result of that. And there was another aspect of that which we'll learn about in a moment. But after that, reactor construction, particularly in the United States, ceased, just stopped. Most of these reactors here are built in places like Korea and Japan and India, and then here in China. After the 3 Mile Island, of course, we had Chernobyl, and then, of course, we had the Fukushima Daiichi accident. Right. Let's talk a little bit about small modular reactors. Oh, the driving force for small modular reactors originally was safety. And the 3 major accidents that we had were the Windscale reactor. Now, this resulted in me becoming a nuclear scientist. I was living in the Isle of Man, and anyone who lives in the Isle of Man will tell you, you can just go to the coast and look, and you can see Windscale. In 1957, I was just entering the secondary school, and we of course suffered by the clampdown that happened, which I'll describe in a moment. A couple of years later, a sixth former gave a lecture on nuclear power, and I attended that, and I learnt about fission and reactors and things like that. And I thought I'd wanted to become a doctor, but I'd actually been dropped a class and I stopped Latin. And at that time, you couldn't become a doctor without learning Latin. So I decided, after hearing this lecture, I would become a nuclear scientist. And I answered an advert in the Daily Mirror for training to be a lab assistant at Harwell. And I went and trained as a lab assistant, and then they paid for me to go to university. And here I am today. So if it wasn't for the wind scale accident, I wouldn't be here talking to you. So this was a plutonium generating reactor. It was operated at low temperature. And as the graphite experts in the room will tell you, if you do that, you build up radiation damage in the graphite, and you store a lot of energy in the graphite. And eventually, if that energy reaches a critical mass, it will start to drop out and be released. And that will heat the graphite, and that will make it happen faster. And then all the energy will come out, and the graphite will get very hot. So they realized that would happen. This Wigner energy was well known. So they had a procedure where they would stop the flow of coolant in the reactor deliberately when a critical level of the Wigner energy was released, so that they could release the energy and prevent it from causing an accident. But the net result was they caused an accident. And people thought it was the graphite that burned. It wasn't the graphite. It's actually bloody difficult to make graphite burn. Anyone tries it, I wish you luck trying to get it to burn. It was the aluminium fuel and tritium with lithium slugs that caught fire, that caused the fire. So not only producing plutonium, they were producing tritium to go into hydrogen bombs as well. And there was a release of volatile fission products. 3 Mile Island, there's only one way to describe it. It was a cock-up, complete cock-up. There were a series of system faults. When you have faults happening in a reactor, sure as eggs are eggs, the operators will also make mistakes. They'll close the wrong valve, or one of the other systems will not work properly. It's better not to have the initiator happening, because once an initiation of an accident starts, it quite often just continues, and you end up by melting the core in the reactor, which is what happened in 3 Mile Island. However, through prompt action by the operators, they did save the reactor from breaching its containment completely. However, a lot of fission products were released. And then we got the Chernobyl accident. This is a scientist's accident. What happened was that they wanted to study the low power operation of the reactor. So they took the reactor down to very low power and then operated for a while. And then there was a demand for the reactor to come back up to power. So they pulled out all the control rods, and the reactor was poisoned. That means xenon isotopes had built up, which strongly absorb neutrons. As the reaction occurred, the xenon poison was built up, and then the power started to rise very quickly. So they dropped the control rods in. However, the tips of the control rods had graphite leaders. So the first thing you put into the reactor was not an absorber. What you put into the reactor was actually a moderator, and the reactors went prompt critical. However, as you boiled the coolant away, it had a positive void coefficient. So even though it was prompt critical, the reactivity rate continued to rise at an ever increasing rate until the whole of the reactor blew the head off the reactor. Dreadful accident due to scientists interfering and bad design. Fukushima accident. Well, of course, we all know that was caused by a tsunami following an enormous earthquake. Many more people were affected by the earthquake and the tsunami than they were affected by the nuclear accident. But unfortunately, the reactors, in 4 reactors that were operating at the time, were inundated with water and could not be cooled. And as we know, we had melt-throughs. Next slide, please. So these 2 accidents were class 5 accidents, not the worst class, but there were fission products released. I didn't have any milk to drink for a month in the Afghan, but at least we didn't get cancer from iodine, so radioactive iodine, because we didn't have any milk. And then we have the 3 Mile Island accident. Again, it was a milder accident, but it was worse in terms of its release, on terms of total release, but less on iodine release. Iodine, of course, is volatile, so it spreads quite easily when it's released after an accident. However, these 2 accidents were severe, and enormous quantities of both iodine and other fission products were released into the atmosphere. However, direct deaths that occurred from these accidents were... I'm overrunning time, aren't I? Right, so these accidents didn't actually cause many direct deaths. At least 11 deaths on the Chernobyl accident, because brave firemen and other workers were put in to try and clear up the mess and limit the effects of the accident. And those people got heavy doses of radiation and sadly died. In the case of Fukushima, 1 site worker, maybe. That's very controversial, whether he might have just had lung cancer from smoking cigarettes, I don't know, but maybe 1 site worker. However, the main impact of the Fukushima accident was on the people who were evacuated. And because in Japan, an easy way of solving a problem is suicide, we think maybe there were 20,000 suicides as a result of people relocated by that accident. So there could have been as many as 20,000 people who died as a result. But that's very controversial. But as you can see, even though the accidents were severe, the impact on the general population was not so great. Now, if we look here, we see that this is the 1970s. Suddenly, the overnight construction costs, this is America, the purple ones here. These are the reactors that were being built at the time of the 3 Mile Island accident. This is the cost of the ones that were built before the accident. The ones that were frozen, delayed, safety measures were built into them and restarted. Their cost went through the roof. After that, you don't get any American reactors until 2023, where at that point is actually not here, it's out here somewhere. But what do we see? Voitel 3, look at its cost. In terms of 2010 dollars, that's the value of the dollar in 2010. So all the dates are renormalized against 2010. We go from $1,000 per kilowatt hour to an enormous. There was an interest in building smaller reactors started in 1990, mainly as a result of the Chernobyl accident. And the reason was not the cost, but the safety. So these interest in building these sort of reactors was in order to put in safety measures. For instance, with a smaller reactor, you can have systems which are don't require engineering intervention, so you get natural circulation and things like this. However, the actual thing that killed the reactors was the price, rather than the safety aspects. But the driving force initially was safety. So, the thing that we were interested in was integral reactors. Now, to understand what an integral PWR is, this is a normal PWR. There's the reactor here, and it has loops with the steam generators, the pressurizer, and the pumps outside the reactor. So what you do in an integral reactor is you put it all inside the reactor. Now, that has a number of advantages. The pressure vessel, unfortunately, is very large and expensive. However, the neutron dose on the vessel is lower because it's a bigger diameter. It's got more water in it. It's got more water in it, so you can actually in the pressure vessel, so you can cool the reactor by making sure that you can take away the insulation on the vessel, and you can just cool it externally. For instance, by putting it into a water tank. So, for instance, some integral water PWR designs actually keep the containment vessels actually in water. Now, the steam is produced inside the reactor, inside the modular steam generators, which are built into the reactor, either around the core, in which case the reactor is very fat, or above the core, in which case the reactor is very long. And this means what's coming out of the pressure vessel are much smaller steam ducts and not large ducts that you get in a PWR. So the welds are smaller, and it's much less likely that you would get a failure of the pressure vessel. Next slide. So I did another of these GIFs, which just show you that what's happening. This is all of the hot stuff is going on inside the reactor. You're putting in cold water, you're getting out steam. It's like a BWR, except it's a PWR inside a BWR. However, next. The first one of these was a design started in the United States by Stone and Webster, who were taken over by ABB, who were later taken over by Westinghouse, Rolls-Royce, and the UKAEA. And I was friends with the UKAEA guy called Mike Haynes, who was actually in charge of this program back in 1990. And this was the first of these designs. Westinghouse bought out ABB and started a program called the Irish program, which was for an international project, which involved a number of countries, but they didn't build a reactor in the end. But they made a very advanced design. And the picture you saw earlier of an integral reactor was actually from the Irish program. A lot of IPWR concepts were started in various sizes. France, Russia, but none of them got built. Two, except for two. An Argentinian program called CAREM, a demonstration reactor is being built. It's being built now for 12 years. For a small reactor that's supposed to be built in 4 years, that's quite a long time, isn't it? That's going to be commissioned maybe, if we're lucky, in 2028. And the Chinese started their project in 2012, didn't start construction until 2021, but that's due to come online in 2026. So those are the only two actual IPWR projects which are still going on. What's happened instead? Well, people have looked back and said, well, actually, these integral reactors are going to take a long time to develop. Why don't we take existing designs and just make them smaller, like we used to do when they were cheap? And so we've got the Rolls-Royce UK SMR, which is a two-loop ordinary PWR. We have the AP300, which is an AP1000 with one loop. So the Westinghouse closed down the IPWR program and are now looking at making just small ordinary reactors. So we've had a huge shift away from advanced technologies to the only advanced part of these reactors, apart from being small, is that they will have modular construction. So they will concentrate on doing all of the work in factories and then delivering them on site so you can plug and play, so that you're not having very long periods of construction. The Russian Design Bureau, Afrikantov, has multiple designs, none of which will ever be built. So why would small reactors be cheaper than big reactors? If we look at the top curve, this is the conventional economy of scale, and that is that the bigger a reactor gets, the cheaper it should be in per unit power, because basically you need less of everything as it gets bigger. For instance, if you take the shielding around the reactor, the shielding is at constant width. So that means for a big reactor, you have it doesn't scale as the power 3. It scales at something like the power 2, but the cost scales at power 3. So the next thing you see is that it's actually to power 0.3, dropping in cost as it gets bigger. So that's the conventional view. So why should it be different? Well, one of the things is that small reactors take less time to build than big reactors, we hope. And certainly in the past that was true. And what we can see now is that we can get a reduction in costs just from the interest that you're saving on the construction of the reactor. The second thing is that the investment cost is lower because they might be perceived as less risky, so you can get a better rate of investment. So the discount rate might be lower. And certainly the size of the investment is lower. The unit size of the investment's lower, which means that you might be able to find a wider range of investors and get a cheaper one. So you can get a reduction on the investment costs. And already we're now seeing that that as we go into this range here, that we're actually below this figure here. So it's actually cheaper. Now, if you then add modularization, which means you do the work in a factory rather than on a building site, one of the problems we have in the UK is that we have huge numbers of contractors doing different things, getting in each other's way, and it takes longer for them to build something. Do it in a factory, get it all assembled into a module, deliver it to the site, plug it in, and off it operates. So again, we can make it cheaper by modularization. And then, because they're smaller, you build more of any one type than you would make if they were bigger. So that means you get a learning process, and that learning process will result the costs. Then the last one is heat. If you can get a payment for the heat, the waste heat that you get from the reactor, which is probably easier to do with the small reactors than it is with the big reactors, then you get a big decrease. And we might see that the final cost per unit power, the levelized cost, could be less than a half of for a very large reactor. That's the theory. Right. Why AMRs? Now, what's an AMR? In the UK, we've got this as an anomalous system where we say an SMR is a light water reactor, which is small. An AMR is an advanced modular reactor, so we're using advanced technology. The rest of the world says that's just an advanced SMR. So this is UK. You press the next slide. So why should we be interested in advanced modular reactors? Well, one of the most important things is higher temperatures. If with the light water reactors, you're limited to 300 degrees centigrade or less for the heat that's coming out. For most of the applications you might want to use that heat for instance, just to generate electricity, it's more efficient to use a higher temperature because at 300 centigrade, you may be getting an efficiency of 33% efficiency. If you go to 700 degrees centigrade, you might get 50% efficiency. But if you want to make steel, we're using a reactor, or glass or cement or something like that, the nearer you can get to 1,000 degrees centigrade, the better. So that's the first thing. There's also, we've just published a paper which is looking at the impact of cogeneration on being able to support the grid. So there's a big incentive to develop cogeneration because most of the energy that we use in industry is not in the form of electricity. And a lot of the things that are done by fossil fuels could be done by either electricity or by using the heat from reactor systems. So we can expand this range of activities. And then high quality heat networks and the storage of the heat is much more efficient and cheaper than storage of electricity in batteries, say. The downside is that as the temperatures go up, the materials you have to use change. You have to take into account creep and stress corrosion and things like that, and it becomes more difficult. However, in the additional slides which are available in the slide packs you can get afterwards, we actually look at what happens if we use certain of the AMR designs, because there's already a huge amount of experience, particularly on high temperature gas cooled reactors and sodium cooled fast reactors. Closed fuel cycles. Well, you'll see in a minute that eventually we're going to have to stop using open fuel cycles and stop creating plutonium mines by burying spent fuel, basically. That fuel is actually a valuable resource. And as you'll see in a subsequent slide, unless we do something about this, we're going to run out of uranium very quickly. Then there's safety. There's no particular reason why AMRs are safer than light water reactors, but the indications are that from the experience with, in particular, HTGRs and molten salt reactors, it should be possible to make them walk away safe, which is certainly not the case with PWRs and BWRs. The other issue, of course, is that things like sodium are not compatible with air and water, and they present additional safety issues. And then the costs, again, the review of the costs of these reactors, some of which have higher power densities than light water reactors. Well, most of them have higher power densities than water reactors. A lot of them, like sodium fast reactors, lead fast reactors, and molten salt reactors, don't need a pressure vessel. They can be contained at low pressure, and that's cheaper. So there is an indication that AMRs will be cheaper than light water reactor SMRs. Right, now, I'm a virgin on AI. So I thought that I would use it for the first time. So I got an AI system to do this slide. So what happens with the sustainability of nuclear power? Now, if we use uranium in ordinary reactors, generation 3 reactors, and we don't recycle it, how long do you think that uranium will last? Now, I've taken an extreme case here. I've taken the total global energy consumption, and I've looked at how long using the resources which have been identified, accessible resources of a particular fuel, how long it would last if we were burning that amount of energy per year. And we see that for coal, it would last about 25 years. For oil, about 15 years. Gas, about 15 years. Uranium, 13 years. 13 years. Not very sustainable, is it? The big shock, I think, for Anika, oh, she's gone, is she? If you're using tritium from lithium-6, 300 years. Oh. So we're going to have to do something about that. Now, if we take the uranium and use it in a closed fuel cycle, it would last nearly 800 years. Now, of course, these are available, identified resources we have at the moment. In the past, with time, these resources have increased. So these are pessimistic figures. So it's going to be more than this. We don't know how much more because we don't know how much we will discover. But if you look, for instance, at how much uranium is in seawater, now it's pretty difficult to get the uranium out of seawater because it's in such low quantity. But for instance, if you were taking other minerals out of the seawater using adsorption techniques, a byproduct might be uranium, for instance, you could make the uranium last for 10,000 years, maybe. But if you close the fuel cycle, it would last for 500,000 years. So my point is, stop burying your bloody spent fuel and creating plutonium mines, because you're going to have to dig it up again if you do that. So the Finns and the Americans and other people, take heed. Now, if we just look at the history, we built up huge stockpiles of uranium. These stockpiles are nearly gone. We predict that by 2030, they will be gone. And at that time, we're going to have to open new mines. The price will go up. Nuclear power will be more expensive, maybe not so extremely expensive, because the fuel cost is quite low compared with the cost of constructing the reactors. But we're going to have to do something soon, and certainly before the end of the century. To press the button again. And by 2070, I think we're going to have to close the fuel cycle. Next slide. So in the rest of the slides, which I'm not going to present and keep you here until tomorrow, you can learn about what's the history of advanced reactors. Let's just say that for both HTGRs and sodium-cooled fast reactors, there's a huge mass of information from past experimental reactors and even quite large prototype reactors, which is available. And that's often ignored by the new designs which are coming out on these sorts of reactors. They need to take into account this history. Next slide, please. And you can see here in terms of high temperature gas cooled reactors, there's operational experience of greater than 83 years of operational experience for HTGRs of two different types, prismatic and pebble. And for sodium cooled fast reactors, again, something like 275 years of experience there on operating power generating reactors. Right, these two slides just show you if we were using LWRs, how we might use them for making cogeneration. It would take me forever to go through this slide. So at your own leisure, have a look at that. And then this is the case if we move to the advanced reactors, where we can expand the range of different things that we can do with the heat from the reactor. And as a byproduct, we get two byproducts. One is we can support the grid at times when the wind is not blowing and the sun's not shining. That's a big problem that we've got to be able to do. And not only that, excess electricity from wind and solar could be used together with nuclear heat to make low-cost hydrogen and other things. I'll just show you this very quickly. There's been a crisis in regulation. What happened in the Reagan's time in the United States is the decision to deregulate, privatize, and to generally turn economies away from public spending. And what's the result? And also the Chernobyl accident. People stopped spending money on nuclear research. And we're only just starting to come out of that period now. We've had a period of maybe 30 years of low expenditure. Organizations like the UKAEA are gone. NNL struggles to find a funding from the government at the moment and get the status of being a national laboratory. We've got to, this is public spending. Private spending is very variable. The public spending underpins the research and ensures that safety and environmental matters are properly handled. Next slide. Even worse with Margaret Thatcher. She hated public laboratories, not just fission, but fuel efficiency, renewable energy. The only thing that didn't suffer was fusion. She essentially closed nearly all of the research which carried through until at the end, towards the end of the Blair regime, it started to pick up again. Because there were many people in the Labour government in 1997 who were anti-nuclear. And it was only the realization that nuclear was going to be necessary in order to meet climate change actions that we needed to build back up our spending. So we're now here, and in real terms, because this is in 2023 money, we're now only about, I don't know, less than half the level of funding that we had back in 1974. This just shows you the various laboratories, that most of which are under decommissioning at the moment. We're seeing some renaissance in Sellafield. I was delighted to see that Berkeley Labs, that was the CGB laboratories, are likely to have a new lease of life eventually, because they made a huge contribution to research. Next slide. This would take forever for me to explain, but basically it shows you the history as we move from the military side with 1954, with the creation of the UKAEA, then weapons being taken off UKAEA, and then BNFL being created from the UKAEA's production side. And then that being wound down into nuclear decommissioning, creation of National Nuclear Laboratory, and then Great British Nuclear here. AEA technology, huge research base, dissipated. Well, the academia benefited from it, but nobody else did really. And then the privatized electricity system, again, research. What happened with research was that the Office for Gas and Electricity Markets had to intervene to make companies actually do their research. So they had a program called Rio. They took money off companies and said, because these were often foreign companies that were operating our privatized public resources for generating electricity and gas, and saying to them, well, if you don't do the research, if you don't make the investment in innovation, we'll keep that money. But if you do it, we'll give you the money back. And they were forced to do research. And of course, that didn't happen with the water system. And of course, our water systems are now in a dreadful state. So we have a real problem in the UK because of the closure of public expenditure. The net result, well, press the button again, of these accidents is that it really killed the expansion of nuclear energy. And if we move to the last slide with the conclusions. Nuclear power, my conclusion from the history is nuclear power is a valuable addition to the range of technologies to manage climate change, particularly if heat is used as well as electricity. 2, the price of nuclear power is the main driver in deciding whether it's used or not. Not whether its emissions are low. We proved that. We can be as low as we like, but things like carbon capture and storage, which results in more emissions, will still always beat it if nuclear is too expensive. We need to get the cost of nuclear power down, and we have a problem with what they call the big project syndrome. We can't, in Britain, anything big overruns and is too expensive. We've got to solve that. Otherwise, it doesn't happen in Korea, doesn't happen in Japan, doesn't happen in China. Why? We've got to learn how to copy those countries. If fission energy is to expand, we need to close the nuclear fuel cycle. Otherwise, we'll run out of uranium. The ability to manage large projects, well, there we are. Main obstacle to rapid expansion is the supply chain and skilled workforce. And of course, you're our future. You're the solution to this problem. So I only hope you're getting a good education here in Manchester. So thank you very much.